All right, folks, this is it. The final formal proofs we'll be doing in this course. Modulo, of course, the second midterm. But the final one's on the homework. That's nice. So what we're going to prove here is that the Levenshtein edit generating function produces optimal edits. That is to say, the total cost of the edits it produces are less than or equal to the edits of any other valid edit. That's pretty cool to me, right? That like, look, we're going to prove that you can't do better than this. That's a great thing to be able to prove, right? Because A, it means you can stop trying, and B, it lets you sort of rest easy knowing that you're doing as good a job as you could be doing. Um, Relatedly, once we've proved optimality, that's a really nice thing for this, right? Then we say that, look, well, if we know Levenshtein, the edit producing function, produces something with minimal total cost, and we know that the total cost that Levenshtein produces is the same as this function, then we know that this function, Levenshtein distance, is going to also produce the optimal number, right? It's going to be the lowest number, which is going to be a good measure for distance. So this is sort of the payoff of having a separate Levenshtein distance function. We're going to prove something talking about edits, and then we'll get to sort of transport it using this lemma. We'll get to transport it to talk about something that just computes distance. All right. Enough with the high level. Let's look at the low level. So as warm-up, we've got some optional exercises, just like getting you with lemmas to talk about the costs of various edit generating functions. These are fairly routine inductions. It's optional, worth taking a look. Next, okay, as another sort of like getting our legs, trying to understand what's going on here, we'll prove that the total cost of subedit is always less than or equal to the total cost of naive subedit. It's never worse. Okay, so that's the first warm-up. This is a proof I expect y'all to be able to do without too much difficulty. Sort of finding the right thing to do here might take a second, but once you've got the hang of it, I think you'll see that it's a fairly routine induction. Okay, now let's do some optimality proof. So the way that we're going to talk about optimality is actually, it's really challenging to think about optimality. So we can see it first here in add empty. So this one's required. Delete edit optimal is not required. Let's look at what it says. For any target strand, if you give me an arbitrary list of edits and edits are valid from the empty strand to target, then, okay, whatever these edits are, I know nothing about them, right? It's just universally quantified, right? We don't know anything more about it other than that it's valid. We know that the cost of the add edit function, the edits it produces, is going to be less than or equal to whatever these are. They might be the same, they might be equal, right? Edit could be exactly added at TGT, right? Like it could be exactly the same, or it could be something equivalent, or it'll be something totally different. No matter what, we're going to be less than or equal. The general approach here is, as you work down, you'll sort of say, well, look, either you can find that they're not valid, right? You can find that like, oh, that's impossible, or you'll find that, oh, it's just doing exactly what added it did, or it's something of the same cost, right? It's not doing you any better. That's the general approach to this optimality proof. You say, okay, well, look, to be valid and optimal, you have to be doing the same work I'm doing. So at that rate, either you're the same as me, you're equivalent, or there's a contradiction. That's the general approach. Delete empty is really similar. These are important practice, important warm-ups. This and the lemmas before are really critical for like getting you good to go. We have one more lemma that we're just going to give you, which ends up being useful. We need it. Saying that, hey, if I give you two of the same things, then it's just the same as copy edit, right? If they're identical. So you can see here some of the way that we're doing reasoning. You can step through this on your own. Okay, this is it. It's kind of big. One thing I want to note is we've actually given you the structure. Right, so like you're gonna do just these cases. We've tried to set you up in each case to have you sort of working in a nice setting, but like not everyone's going to be completely comfortable with what you have. Being patient is really key. You're gonna get big goals. There's like not a lot you can do about it. So I'm sorry about that. There's really, I think, no way out. But I think a good way to go is to just like try to knock off each of these as you can. Maybe give yourself 10 minutes per case, and then when you don't get it, go to the next one. and then sort of keep alternating this way. Eventually, you'll start to build up an understanding. These first 5 are not so bad, right? These are more or less base cases. These 4 are a little bit more complicated. So like the first thing I would recommend is go through here and take a careful look at what our proof is doing. Right? You're gonna have to look at that and sort of be savvy about that. Situate yourself, figure out which case you're in for each of these, right? You can kind of get a hint here, right? You can see here which case you're in for the edit, but then also take a careful look at what you've got, sort of in your context. Again, the general approach is going to be like we saw for add empty optimal, where you either do something equivalent or you're going to have a contradiction with validity. Okay. I look forward to chatting with y'all on Zulip about this and talk to you soon. Cheers, y'all.